again, my name is Jenna. I'm a Built Environment Initiatives Coordinator with the Community Energy Association, where I support high-performance building, training, and industry engagement initiatives. So I'll be facilitating today's webinar focused on real-world lessons and practical strategies for delivering high-performance HVAC and heat pump systems that improve comfort, efficiency, and homeowner satisfaction. All right, so before we begin, I'd just like to acknowledge the land where I'm joining from today. So I'm calling in from what is known as Nelson, located within the traditional territories of the Snaiks Nation, the Silks Nation, and the Ktunaxa Nation, and home to Métis people and many diverse Indigenous communities. As we gather to talk about buildings, energy, and the future of our communities, I want to recognize the long-standing relationships Indigenous peoples have had with these lands and the knowledge systems that have supported stewardship, resilience, and adaptation here for generations. So as part of CEA's commitment to truth and reconciliation, we like to open these sessions with examples of Indigenous leadership in the built environment space. So the Newhalk Nation are located in around what is now known as Bella Coola. And Newhalk housing specialist and advisor Richard Hall, who has 35 years of building experience as an international Red Seal carpenter, recently produced the West Coast Building Standard Residential Construction Specification. So it's a publication he developed in partnership with RDH Building Science and David Wong Sea to Sky Architecture and Urban Ecology, with support from BC Hydro, BC Housing, and the province of BC. So the West Coast Building Standard incorporates recent building science, technology, and practices, including energy efficiency concepts and reduced embodied carbon levels, and most importantly, new designs featured in the guide complement the cultural lifestyles of coastal communities. So one of Richard's intentions with the West Coast Building Standards is that it can be used as a model that can be edited and adapted to meet each nation's unique needs. So again, we'll be sharing these slides out if you want to kind of dig into that a little bit deeper when we do. Just taking a quick moment to extend our sincere gratitude to our webinar sponsor. They sponsored the entire webinar series. This is the third in the series, McDonald Mechanical Limited. Just going to quickly introduce who we are as the Community Energy Association in case you haven't joined us before. Community Energy Association, or CEA, we are a nonprofit that works with local government, Indigenous communities, and industry partners across BC to support practical approaches to climate and energy challenges. So a large part of our work involves supporting the construction industry as building performance expectations continue to evolve. So that includes developing training opportunities, shared applied knowledge, and creating space for conversations like today's discussion, where practitioners can exchange real-world experience and lessons learned. So we've been delivering high-performance building training since 2017 in collaboration with industry associations, educators, and professionals working directly in the field with an emphasis on practical application and implementation. So if you'd like to stay connected to future webinars, training opportunities, or resources, you can visit the CEA events page or sign up for our high performance building newsletter, and we'll include that information in the chat as well. All right, I'm just going to provide a quick overview of today's agenda, and then I'll pass things over to Rob. So we're going to start with a presentation from Rob Pope with Ecolighten Energy Solutions. So Rob's going to walk us through some key considerations and real-world lessons related to high-performance HVAC and heat pump systems. And then following that, we'll move into a facilitated panel discussion with all of our speakers, where we'll dive deeper into topics like right sizing, duct design, cold climate performance, installation challenges, workforce trends, and practical strategies for improving homeowner comfort and system performances. We'll have time at the end of each for Q&A from you folks in the audience. So please continue submitting questions throughout the session using the Q&A function, and we'll ask on your behalf. Okay, and with that, it's my pleasure to pass things over to Rob. If you've joined us for any of these mechanical system focused sessions before, I'm sure you've had a chance to meet Rob. We're really lucky to have him here today sharing his wealth of knowledge. Thanks, Rob.
Thanks, Jenna, and thanks everybody for being here. Hopefully make it worth your while. If not, we have the other panelists who will definitely ensure that that happens. So let's get started. The agenda for today is going to include, first of all, the topic of today's discussion, which is HVAC design and installation, but we're going to put that into some context. Then we'll move on to details in that context, basically the HVAC journey in new construction and, by the way, retrofits. So best practices, and that'll be what we consider the 7 stages of the process that is required to ensure a successful outcome for any installation. Then I'm going to give you a peek into a costing study that was performed, that we did for CEA and ZEVEX, and interesting findings that came from that, regarding costing, regarding budgets and all that kind of stuff. You might notice throughout this presentation on the slides that I highlight anything to do with costs and budgets. And it's because of, the environment we're in today, is a little stressed on the cost side of things, which is tending to impact decision making to some degree. And what I want, hopefully, to come out of this is that what we're about to talk about today, not just me, but all of us, is all about optimizing processes and approaches to actually reduce the cost of installation, or at least not spend more than is necessary. And in the end, of this presentation, I think we'll have like 10-15 minutes to have questions regarding the slide deck that I've presented, and then we'll move on to the panel. So just like anything, to provide an optimized HVAC system for new home construction or retrofits, we need to have a plan. We need to have a plan and a way to execute that plan. And that plan has to have clear objectives, in this case, to meet the expectations of the project. And some of these expectations would be obviously compliance requirements, budget and schedule, comfort and health, aesthetics, performance. When I say performance, both energy efficiency and cost efficiency. Occupant operability, how can they operate the system? Can they take care of it and maintain it? And of course, ultimately, system reliability, a system that they can count on for hopefully decades after it's been installed. And here it is. These are the 7 stages to a quality installation. Now, obviously, this can be broken down different ways. Groups of these stages can be put together, but this is how we like to look at it. And even though we're talking about design and installation today, we have to keep in mind that HVAC design and installation are just 2 parts of 7 parts. And you can't have good design and good installation unless you've done all of these stages, from discovery to homeowner education. The last time you say goodbye to the homeowner after everything's been done, and then you don't have to go back there again unless you're friends. From discovery to the homeowner education, each stage of any project, that's a spelling error there, is interdependent. They depend on each other. Each stage relies on the integrity of all other stages to achieve an optimum outcome. And you can take any of these stages out and everything else will basically fall apart. You can't deliver the finished product to the homeowner unless you've done load calculations, unless you've done a discovery, unless you've done the equipment selection and so on. And of course, done a adequate design and proper installation. They all are interdependent. Unfortunately, across the country, BC is no exception. There isn't really an accepted national standard of practice for HVAC in Part 9 buildings. Part 3 buildings, we have engineers, but in Part 9 buildings, we don't, and there's no professional verification of a standard because there is no standard. And so what do we have? We have a culture of load calculations done by rule of thumb, designs done by rule of thumb. And I find that when there's a good design, in a lot of cases, it's just a coincidence. Most of the cases, it doesn't work. And verification, adequate commissioning is rare. That's when you do the shakedown of the system, make sure everything's working, do the adjustments, readjust the configurations that come from the factory, all that stuff to customize the final details for the project you're on. Usually you find out after the system's installed and the house has been occupied where the failures are. You should find them before the occupants take possession of the house, I think. In these 7 stages, we're going to start with discovery, But discovery is one part of a process that you may have heard called IDP, Integrated Design Process. But the discovery part is usually the first contact with the project team. That's when we take on projects, the first thing we want to do is talk to the project team. Sometimes an architect, sometimes the homeowner directly, sometimes a builder, and so on. Whoever it is that's reaching out to us, that's when we want to find out about the project, ask a whole pile of questions, and get a sense of the scope. And that, if we proceed forward with the project, is the first step, the discovery. And you can see here, the integrated design process, continues on beyond discovery. As you go through load calculations, equipment selection, and the HVAC design, you're still doing all the coordinating with the project team, which by definition is still the integrated design process, IDP. Now, the IDP doesn't have to be a formal process. It can be. I mean, it's up to the project, it's up to the situation. If you're trying to get net zero designation, it probably has to be formal. But either way, formal or informal, it's just about people talking to each other that need to talk to each other ahead of construction, so that by the time you get into construction, you've got the roadmap all figured out. You're not making decisions along the way during construction, which is an expensive way to do it. One of the things we want to know in the beginning of the project before construction is, what are the expectations, usually of the homeowner, or maybe the architect, maybe the builder, whoever. What's the expectations of the project generally, and do they align with budget and constructability? If they don't, which is often the case, something has to move, of course. What can move? How can we balance these two? Where is the flexibility between expectations and budget? You might find that the client, if they can be convinced that it's a cost effective or has value, they may be able to spend more money. Or maybe they can't, in which case the expectations have to move. Something that does, because we need to balance those two things, budget and expectations. And we also want to know who's on the project team. Is there an architect? Is there a builder? Is there an energy advisor? Is there an HVAC contractor? Is there a structural engineer? If all these people are on the team, or some of those people are on the team, we don't want to work with them independently in one-on-one silos. We want a coordination as a team, because that's where we come up with the best ideas, the creative solutions to problems, and the ability to seize opportunities. We need a team to do that. You can see here, there's a little chart on the side here done by a Canadian Mortgage and Housing Corporation. And it's kind of a visual way to look at it. You incur more costs up front when you put that team of professionals together to do all that coordination, to do the integrated design process. But you save on the downstream costs during construction to occupancy. Whereas if you do it, what is traditional, where each professional is working in a silo independent of each other, then the things that come up are going to be costly, affect schedule, and so on, and impact the cost of construction once you start building. So we move on. Say we've got the discovery offering. We know what the project wants. We know the expectations. We've worked out the alignment of the balance of the budget and expectations, and we've got a scope. And now we're moving forward. What we need to do now is do a set of load calculations. F280-12. That is the CSA standard method for the methodology to discover what the heating load and the cooling loads are. What's the equipment capacity requirements? That's the methodology. It's in section 9335 of the building code. It's actually required. It's crazy not to do this on a project. Luckily, it's getting more common that it is done. But rule of thumb still happens. But it's nuts not to do this. And doing this will, first of all, make sure that you're delivering something that's in the end a product that the client is looking for. That's comfort. They want to be warm in the winter, cool in the summer, and they want a healthy, clean environment to live in. That's comfort. And we don't want to oversize, undersize, because we won't be able to deliver that. We want to reduce installed HVAC system costs. We don't want to oversize the system. There's no upside to that. It's going to cost more. It's not going to work as effectively. It's going to short cycle potentially. It's going to shorten the system lifespan, more maintenance repair costs, for example. There's a lot of downsides to not sizing properly, but there's no upside to it. Also, you're being compliant with the code, which is going to be mandatory in most of the jurisdictions you're in BC and across the country and other in many jurisdictions. And the other thing is you want to reduce your liability risk. You don't want to size something with your thumb. Down the road it's not working, and next thing you know, there's problems, and maybe you're in court. Load calculations have to be done in a way that no matter who's doing them, in whichever software you're using, they're going to come out with the same results, reasonably close, with a reasonable variance between them, right? And this wasn't the case not that long ago. Years ago, you could have a software program, including the ones you see down below, and others that claimed to be CSA F280-12, and they'd all come up with very different results. Then a few years back, went through the process of going into the program and software, the math behind the curtain, involving the software developers, and came out with what we call certified software. HVAC Designers of Canada led that. And what that means is that if it's a certified CSA certified software, it's not going to matter which one of these you use. It's whatever is handiest, whatever is the easiest, whatever you have, whatever is most appropriate. And here's a few of them. TECA in BC has a certified F280 load calculating software that is very accessible, doesn't cost much up front, doesn't have a huge learning curve. It's very, very good for contractors. RightSoft is another one. It's a little more sophisticated, has a higher upfront cost and yearly subscription, but it's not just doing load calculations. It's also a software that designers use because it does much more than just load calculations. So it has some value if what you're doing all day long is designing systems. HeatCAD, same as RightSoft. And then there's this thing, VoltaSnap, and we'll talk a little bit about that in the next few slides. So in BC, we've got the energy step code and the zero carbon step code. Across the province, we have to comply with these step code requirements, among other compliance requirements from the jurisdictions with authority. Throughout the province, we have to comply with these. In order to do that, the project has to have a certified energy advisor, an EA. And incidentally, that EA should be part of any IDP team, any integrated design process team. Now, the EA is going to use HOT 2000, that's Enercan's software, to model the energy performance of the building to see if it complies and to get it to comply with the step code, zero carbon code requirements. So it's taking information about the building, all the assembly details, window R values and U values, solar heat gain values, and so on. Basically, the parts of the building that affect and impact energy performance. It puts all that into this program, and then it does its calculations. Now, this is really helpful for the HVAC designer because this has to be done anyways, the HOT 2000 report. So HVAC contractor can, if you're coordinating with the EA, and you should be, is take those, the data. They can just literally take that report that's already done, has to be done from the EA, put it through this program called VoltaSnap, and it'll automate the process of delivering what is non-compliant, that HOT 2000 report, and making it compliant. You'll do the adjustments and everything necessary to make it compliant. And it's been tested and certified to do this as Volta Snap in Hot 2000 marriage, that it works. And so imagine you're an HVAC contractor, you just coordinate with the EA on the project and put these things together, and now you have a set of load calculations. That is a pretty simple way to go and very cost effective. Or the other way to do it is the assembly details, they have to be coordinated between the builder, the architect, or whoever. Anyway, they exist. You don't have to recreate them. You can take those assemblies, just ask for the report, and then input them yourselves into the program you prefer to use. So, for example, we like to do our own load calculations. We wouldn't use VoltaSnap because we're using a program that that has many more functions as load calculations. But we want that in our program so that we can design the system. But again, it still saves a lot of time rather than looking up the R values of each wall and assembly, each window and all that. That's already done. Might as well use it. So you've done your discovery. You've got your scope sorted out. And you've done your load calculations. You've done whatever coordination you need to do to get the load calculations to F2012. And now you can go to the next step. And you can't do it unless you complete those two stages. You can't get to this step effectively, that is. And this step is equipment selection. Okay, we know what we need to do. We know what they want. What equipment are we going to choose? And there is a lot of varieties, not just equipment, but technologies. We've got air-to-air, for example, forced air systems, or ducted and ductless cassettes. We've got air-to-water systems, mostly for radiant, but it's also used for radiant with forced air and domestic preheat. We have domestic hot water heat pumps, split and packaged. And we have ground source heat pumps, often referred to as geothermal, which is water to water, and water to air. And it goes on. There's different refrigerants. There's a lot of product out there. So what to choose? Well, one of the first things that'll impact that decision, which equipment to use, is going to be how you're delivering the heat or the cooling to the building. And if it's a hydronic system, that's going to be one thing. If it's a forced air system, it's going to be a different thing, or both. And both is not uncommon in the Vancouver area, the Lower Mainland. Whistler, for example, very common, where you've got an air-to-water system doing both radiant heat and forced air cooling, and some domestic hot water, among other things. So that will determine to a large degree what type of equipment you're going to use. And then beyond that, how to nail down specifically what equipment you're going to use, you're going to take into consideration budget. So you can go to, like anything, there's going to be a spectrum on one end where you're going to get the most inexpensive products on the market, and the other end, the most expensive. And there is some loose correspondence to the quality, not always, between the least expensive and the most expensive. It's not always perfectly correlated. So, but depending on the budget, that'll have some impact. Zoning capability, cooling capability, indoor air quality and health, ventilation, integration, installation and maintenance, space limitations, aesthetics, noise level. These are the kinds of things that's going to kind of hone you in on the product you want. Besides the fact, if you're an HVAC contractor, you might just already have a relationship with a supplier or a manufacturer that you use their projects exclusively anyways. Once the distribution system has been selected, as I said, here is a list of what's going to be in play when you're making your decision: cost and capital, operating expenses. If the client is that's their forever home, your operating costs will, if they're effective and efficient enough, might affect their decision regarding the capital costs, and vice versa. If there's a short-term thing, it might be the other way around. Capacity and suitability for the home, equipment efficiency, installation and maintenance requirements. You get a complex system, it's going to take more to maintain that, take care of it, obviously. And other things, space requirements, noise, electrical service requirements, etc. Okay, you've gone through all that. You've selected the equipment. The next thing is the balance point, and I can't understate the importance of a balance point. Without the balance point, you're kind of flying blind in terms of what equipment is going to do for you at design conditions, not nominal capacity and efficiency, but at those winter temperatures that you're going to be designing for, or at those summer temperatures that you're going to be designing for. The balance point will tell you that, and now will help you determine which equipment, which model, which size of your choice that you're going to use. So heat pump has a nominal capacity. It's usually a 47F, which is about just a little bit more than 8 degrees Celsius, I think. That's its nominal capacity. So a 4-ton is a 4-ton at that temperature. But as the outdoor temperature decreases in the winter, that heat pump's nominal capacity will also decrease. Now, how much it decreases, how fast it decreases, the steepness of the curve or flatness of the curve depends entirely on the equipment technology that's being used and the quality of the heat pump. So between like a good quality cold climate heat pump and a inexpensive single stage heat pump, there's a massive difference. Calculating the thermal balance point requires just the heat loss of the home plotted against the performance curve of the heat pump. Now, I don't want to get into that too much because that's into the technical weeds and we could spend a whole day talking about that. But just at the high level, a balance point has to be done. A balance point has to be done. That's the thing to take away from this. And here's another thing. I've heard often that a heat pump works to this degree, and then you need your auxiliary heat or supplemental heat, your backup heat, however you want to call it. But it's actually that's a myth. That there's no such thing as a universal balance point. Every manufacturer and the product lines within that manufacturer, the models, all of them have different performance curves. And so you could never get a balance point that is universal. It just doesn't exist. You won't know until you actually go through the process of discovering what the balance point is for the equipment you're thinking about using. There's 2 types of balance points. There's the thermal balance point. That's the temperature at which the primary heat, your heat pump, can't keep up anymore, and something else has to either take over or assist, depending on whether it's dual fuel or all electric. Then there's the economic balance point. That's the temperature at which it's not any more cost effective for your primary heat from the heat pump to deliver the heat. Now the auxiliary will be more effective. That depends on the efficiency of the equipment and the cost of the energy. And it's different across the country. The economic balance point is not really something that we concern ourselves with too much in BC because our cost of energy is pretty favorable. So it's the thermal balance point that is more important, and that's what we focus on. So I'll just go through this a little bit. Again, equipment selection, selecting the most appropriate equipment based on performance and cost. Can't be done without knowing the balance point. The electrical panel, especially if you're going to use all electric system as opposed to dual fuel, the amount of auxiliary heat you need needs to be figured out because that'll affect the size of your panel. And if you're working under restrictions, say it's new construction, it's not unusual to have a 200 amp panel, and in a modern home they want everything in there that's using up quite a bit of those 200 amps available, and you want to put in 10, 20, kilowatts of electric heat, that's going to be an issue. So it might not be, but you don't know until you do the math and figure it out. You can't do a cost benefit analysis properly, a feasibility of one choice versus another, unless you know the balance point. And system optimization. Balance point is a critical tool that you need to deliver the best value in both comfort and affordability. There's just a few steps you need to just go through them quickly. You need the load calculations. You just need to select the heat pump technology. You hone it down from all the available products and technologies out there. You hone it down to what you'd like to put in. Find the performance specs of the equipment, plot that on the graph with the heat loss line, and what will happen is the equipment performance curve will intersect somewhere with that heat loss line, and that's where your balance point is. Also, equipment selection. What we would like to do is ensure that the equipment, because whatever kind of system you have has a number of components, we want those components to be able to talk to each other, transfer data, and use the algorithms in the equipment and to optimize the equipment's comfort and efficiency performance. That's the ideal. You don't have to do that, but it's a little trickier when you have mismatched equipment. There's proprietary control in some of the high-end equipment that is really effective. It doesn't mean that optimization of the system is exclusive to those kinds of systems, but it's easiest. Matching systems is better than non-matching systems if you can do it, but it's not the end of the world if you can't. It's still okay. So when it comes to design, and this is the subject of today's workshop, so I like to think we can guess or we can design, right? It's one or the other. And whether it's new construction or retrofit, a heat pump is ultimately a controlled refrigerant cycle, and it's using things like phase changes. It's going gas to liquid, and so forth. And for it to work properly, because it's pretty finicky, it has to have a well-designed system. It has to be connected to a system that actually is going to, help it do its refrigerant functions, help to make that refrigerant cycle function properly. So you got to have the right amount of airflow, and you got to have a system that's able to deliver the energy that it's trying to create. Poor design has many consequences. I could show you for weeks, one photograph after another, all day long, every day, of things that have gone wrong that I have seen myself personally, let alone the ones that get sent to me or the ones that I've seen from others. It's just no end of the consequences that can happen if we don't design properly. One of those things is decreased capacity. Higher cost, reduced performance equals higher operating costs, maintenance and troubleshooting costs, potential equipment replacement costs, system failure, nuisance tripping, potential evaporated frosting, reduced circulation, compressor damage, and so on. There's a long list of consequences to poor design. Good design, on the other hand, when it comes to forced air, can use low, medium, or high velocity ducting systems for the distribution side. And a design will look like something like this. It depends on the budget, of course, and the complexity of the building, and a whole bunch of other things that you will learn during the integrated design process. So you can do a single line drawing, you can do a two-line duct design. You can even do a three-dimensional if the project wants that and can afford it. Incidentally, I think probably 10, 15 years from now, that three-dimensional design will be the standard approach, and people will be talking about the 2D design that is the most prevalent now, as we talk about the handwritten designs from 20 years or 30 years ago. It won't be long before 3D is the go-to way to do it. Now, there is not a universal in Canada definition for Part 9 of what a designer is. Who is a designer? I mean, you just call yourself a designer, now you're a designer. Or what a design is. And this is what we say. Design should include the design intent and standards of practice. It's one thing to beautifully lay out the ducting and the hydronic piping and all that. But if it's done with a very poor standard of practice, it's not going to mean anything. The standard of practice should be in the design intent. The design should include that. Of course, equipment schedules with brands, models, capacities, efficiencies, electrical specs, and field settings should be in the design. That's what we think. A schematic arrangement of the system showing ducting, piping, fitting, airflows, and more. Where's everything going? What size is it? How's it getting around that beam? How's it going to terminate? Is it going to be, a nice discrete reveal above a cabinet, or is it just a standard off-the-shelf grill? Every little detail should be in the design layout, including airflows and everything else, so that you can measure eventually the performance of the installed system against the intended performance from the design system. And finally, detailed section views for clarity. Because when you're looking at the top view of any design, it can get pretty cluttered and hard to make it out. So what you want to do is take those, heavy traffic areas of a design and break them into sections so they're easy to understand. Installation. As a designer, we like to assume that there is a handoff between the designer and the installer. And that handoff is roughly, although it's a moving target, where the installation manual begins. We have to make some assumptions that the installer is qualified to do the installation. Now, that's not always the case. Sometimes it is. But that's generally speaking the handoff. As far as installation practices go, particularly with heat pumps, we want to make sure that the entire length of the refrigerant line is insulated to avoid condensation. All penetrations to the building envelope should be sealed with insulating sealant in spray foam. Those are pretty intuitive standards that anybody should expect, but you'd be surprised how often they're not met. The outdoor equipment should be above the snow line. Like we work in places like in Vancouver, where our snow line's relatively low. You still got to be above it, but it doesn't happen very often. Whereas in Whistler, you've got to be 8 feet above the floor to because they get that much snow. I'm exaggerating. It's not that much, but you have to be above the snow line, or you're going to impair the function of the outdoor unit. You want it away from drip lines. You want it from roof overhangs, for example. This is another thing we don't see often enough, and we're very, very strict in our designs and our expectations that they exist, is vibration isolation. And that equipment's got a compressor, fan in it, among other things. It's going to move. Even if you can't see it moving, it's moving. It's always moving when it's running. What we wanted to ensure is that the amount of movement, the degree of movement, doesn't impact its internal circuits and components. So we want some isolation. Plus, we don't want the potential movement on something of a hard surface to amplify any potential noise. Obviously, we got to be in compliance with local bylaws and adhere to the manufacturer's clearance requirements. One way to install it or ensure that we're getting what we want, we design a beautiful system. It's award-winning design, right? But if it's not installed properly, that's going to be an issue. One of the ways to avoid that being an issue is we do field reviews. We do mid-construction field reviews. Often, in our case, we'll do a walkthrough when the building's up and ready for installation, just to make sure that we align with mechanical contractor, the builder, in our own designs, that everything's lined up. We might tweak a few things at that stage, but more importantly, before we cover everything up, we're going to need to do couple of things. One of them, there's going to be a blower door test, right? So there's a mid-construction stage that requires kind of an inspection. What it is the mid-construction blower door test will check the building envelope to make sure it's going to meet the target that's required for compliance. In other words, it's not too leaky, and if it is, we can find the leaks and fix them, right? Around the same time when that's happening is the best time to be doing the mid-construction HVAC system field review. That's when we want to see everything's roughed in. Doesn't have to be completed in the mechanical room yet. It'd be nice if it is, but everything is going to be covered. We want to have a look at it and just make sure that it's installed as designed, or at least meeting the design intent if there are variations from the design. This is one of my biggest pet peeves here. Is there's very few contractors do this. I don't get it. I don't know why they don't, because to me, you're not a pro unless you're doing this. And that's doing the performance verification. It's sometimes called commissioning. This is, as I said earlier, the shakedown. You want to check everything. Make sure it's all working. There's default settings that you might have to adjust. There's components that might be failing, and it's a simple warranty issue. You go to the supplier and get it replaced. And you want to balance it, and you want to make sure that you're following, for at least warranty purposes, the startup procedures required by the manufacturer. And you want to document all of that stuff. So it's there on the record. It's your benchmark for future technicians going there to do maintenance or repairs. With refrigerant systems, these are the kinds of things that need to be done. Nitrogen pressure test, vacuum test, verify refrigerant charge, run the startup sequence, etc. For ducting, you want to measure total external static pressure, measure airflows, adjust control settings, calibrate and fine-tune the system where needed. So there's a process, right? It's not just show up, turn things on, listen, see, oh yeah, okay, it's running, and then pack up your tools and go. And one of the ways that you can tell that the technicians that are there are actually doing a proper, thorough commissioning is what they show up with as far as tools. They need these tools, as you can see here, to do a proper commissioning. As opposed to, and I've seen this done where, somebody goes, finds a piece of toilet paper, and then they put into a little strip, and then you hold it over to the register, and oh, look, there's air movement. Okay, we're good. And then off they go. No, there's a lot more to it. This is really critical, very important. You need to do all this stuff. And if you don't have this equipment, then you can't do it. Homeowner education. Okay, this is a newly installed system. And, most homeowners really don't know what they have. They kind of, but they're not us. And that's the reason they hire us. So they don't have the technical understanding of everything that's there and how to operate it. We got to give them the overview. We don't need to teach them how a refrigerant cycle works, but we have to teach them and show them where your heat pump is, how to clean, how often to clean it, especially if it's under pine trees, you got to keep the pine needles from accumulating on it. Change the filter, where to change the filter, where to get the filters from, and that kind of stuff. How to operate those thermostats, the program and schedules and so on, know what the difference is between fan on and continuous fan mode, those kinds of things, and why those things are important. There's a lot of times where a contractor, and even me, will get a call because something's not working. We show up and it's just that they were never showed how to operate the system. They got it programmed wrong or something like that. We want to avoid that kind of stuff, and we want to give the homeowner some sense of not being vulnerable to the system. It's too complex and scary. We don't want that. We want to make it easy for them. We also want them to know where all the paperwork is, and included in that paperwork is user manuals and warranty paperwork if required. The documentation left on site should include the designs and as-built when there's been deviations from the design. All equipment submittals, installation manuals, model serial numbers, so on, all warranty documents, final commissioning reports should be there, all user manuals, maintenance schedules, and procedures for all equipment. That should be in the documentation left on the site. Okay, we're going to this costing study now. I'm not going to go through it in detail, but I'm going to give you some of the things, the highlights that we discovered. It was very interesting. So Zeke and CEA conducted an outreach process to general contractors and homeowners across BC to obtain costing data for recently completed projects. So ultimately, there was about 20 of them, and they were all over the province. They were all different kinds of houses, many different builders, many different climate zones, and step code levels, so on. So it was a nice, quite a good variety. These were all built between 2020 and 2025. You can see some of them here. So what we did is we included here, among other things, and this is a total living area within the envelope, climate zone, BC Energy step code, rated efficiency of the equipment that was installed, month and year build, installed costs, and we converted those installed costs to cost per square foot. Now the installed costs were very specific to the mechanical contractors invoicing. So not the quote in the first place, is basically the end of project finish, what was invoiced for the supply of the mechanical systems, all the HVAC systems, and the installation of all those systems. Those were the basis for these installed costs. And one of the interesting things we found is that across all metrics, it didn't matter. Size didn't matter. Efficiency didn't matter. Climate zone didn't matter. Step code didn't matter. All of these costs clustered in the same group between $12 and $17 per square foot. Now, if you're a builder, homeowner, and you're within that range, then you're okay. Now, if you're wondering why you're at the high end of that range, you should look at the system that you're wanting to put in. If you're at the low end of that range, it's probably good. Things affecting the costs, competitive market dynamics in the area in time of build. I mean, if you're the only contractor in town, it's going to be a big difference than if you're, one of a bunch of contractors trying to get the same job in Vancouver. Size and complexity of the house design and corresponding HVAC system obviously affects the price of the HVAC installation. The degree of custom versus off-the-shelf ducting. Now, we've dealt with architects mostly that say, no, we don't want drops. Or can you put it in a 3-inch ceiling drop? We want a fur-out walls. Can you fit it into the wall? And so on. Often what you're doing, and when cost is not a big driving factor in the HVAC budget for the project, you'll just, you can make it work under surprisingly restricting conditions if you're creative enough. But what you're doing is you're customizing every single fitting. There's a lot of customizing, and it costs an awful lot more to use customized materials on a job than it does to use off the shelf. So if you're wondering why the cost of the HVAC is so high, that's one of the things to look at. Sophisticated or simple controls. You want to integrate it with a whole house automation system. And you can multiple zones, and you may have a combo system, cooling, radiant heating, all that stuff. The degree of complexity of the controls will affect the price quite substantially. The standards of practice of contractors. Now, in our group, or the group of projects that we looked at, there were outliers on both ends. There were some that were more expensive than others, than the whole group. Just a few outliers, and some that were the opposite. They were just surprisingly inexpensive. When you see something that is surprisingly inexpensive, you got to wonder. they still have to pay for all that material and equipment. They still have to pay for labor. So what are they not paying for? Are they doing it for free? They don't care about margins? No, usually it's the quality of the installation that we're talking about in those cases there. And quality of equipment and materials does play a role in the cost. Cost for equipment more so than materials, because you can get a Chinese manufactured heat pump that works pretty good, surprisingly good, I hate to admit, compared to a Japanese top of the line trend-setting piece of equipment at the other end of the spectrum with solid reputation. You can count on it, but it's going to cost a lot more money. But there may be a value proposition that allows you to choose that expensive one over the inexpensive one. And I wanted to show you this. There's a project in Vancouver. I don't know why. Well, I kind of know why the builder did this, because the builder is also a developer and a homeowner of this home. And I guess he thought it would be fun or an interesting exercise. But nevertheless, he took our coordinated, detailed, final set of designs, specifications, and use them as a bid spec to get quotes from contractors, mechanical contractors. 10 of them. I happen to know 9 out of 10 of them. At the time, I know them all now. And this is the range. As you can see, there's quite a variability. Now, I can tell you contractor number 10, he was busy, didn't need the job. That was his quote for that reason. If he got it, it would have been worth finding time on the calendar to make it happen. That's all that was about. And that happens in a busy market. Contractor number 1, I can tell you they would have lost money, because unlike a lot of projects, I would have been watching them like a hawk, and they wouldn't have been able to get away with cutting corners on one of my projects. And so they would have lost money, or they would have had to renegotiate. It was not a reasonable quote. The average quote was around $50,000, and I think they went with contractor number 5. I can't remember. But this gives you an idea of, when it comes to costing, how important it is to shop around the project to different contractors. And I know that a lot of builders have their team, their preferred contractor. They go to their go-tos on a lot of projects, and I think that's really good. I think that is a sign of a good builder when you have that same team. But if you are cost conscious, you need to get another quote and see what the difference is. Obviously, there's other values in having that same go-to contractor. It's not expressed in dollars and cents, but it has value, and that might be worth it. But I think it is important to get more than one quote, nevertheless. And that's it. We're at the best slide of them all.
Yeah. Thanks, Rob. That does kind of bring us to the time we were hoping to introduce the panelists, but I will ask just a couple quick questions. I think that the rest of the questions that came through would be great to ask all panelists, but I know you spoke to Volta Snap. So I did share a link in the chat, folks, if you want to check that out more. But do you know if it's do you know offhand the cost and if it's a yearly cost?
No.
Okay. All right. So folks, check out the link that
I'm sorry, we don't use it.
No,
So
that's okay.
I'm sorry, I don't have the answer to that. Yeah. I don't even know the cost of the programs that we use. I keep out of accounting for good reason.
No problem. And then I was just going to ask just one more question for you. If you would consider using BIM, building information modeling, for your building design, if you've used that before.
I'm sorry, say that again. Use which?
BIM, B-I-M, a program for your building design.
Well, we've got a lot of we've had a lot of explorations into different programs, different processes, and so on. We're pretty happy with the one we have now. We're working, in Revit now, 3D stuff on the larger custom homes, and just simple AutoCAD on the simpler homes. But I can tell you this, pretty soon we're going to be AIing most of this anyways. So I think I, at this point in time, I'm not really interested in making any investments beyond what we've already done because what I know is coming, because I've seen it, um, is the complete, almost complete automation. Of course, you still need a human behind it, but you're not going to have to do much drawing. You're not going to, you're going to be able to um, harness the capabilities of AI to do most of these designs, and that's going to change things quite a bit. It's going to, it has consequences, but it has benefits. And how you look at it is up to you. But I am in no doubt that we're going to have to embrace that in the next few years, for the next 5 years, I would say.
Okay, great. On that ominous note, no, no, great. Thanks so much, Rob. Thanks for sharing your expertise. Rob's not going anywhere. He's going to stay with us during this panel question. So folks who have asked questions that we didn't get to, I'm just saving them for the end, and then we can ask Rob along with the other panelists. So I'm just going to introduce the panelists real quick. Natasha is going to be working in the background to get them front and center on your screen. So we're fortunate today to have a really experienced group of panelists joining us. They're representing perspectives from HVAC design, installation, distribution, building science, and workforce development. So you've just heard from Rob. Thanks again for a great presentation. Dara Bowser is the Managing Director of HVAC Designers of Canada. He's representing professional HVAC designers across Canada, and he's been involved in residential HVAC systems and building energy use for more than 40 years as a consultant, manufacturer, researcher, and trainer. So Dara is nationally recognized for his expertise in Part 9 HVAC design and performance, with extensive experience in system design, commissioning, research, quality assurance, and fault investigation. Then we have Joannie Kwok. So Joannie is the co-owner and manager of Village Mechanical in Terrace, BC, specializing in cold climate heat pumps and energy retrofits. And her work combines HVAC operations, workforce development, and community partnerships on growing skilled trades capacity in northern BC. Then we have Bryan Allen. So Bryan is the regional sales manager for residential HVAC at the Master Group and has more than 27 years of experience in the HVAC and mechanical wholesale industry. So his experience spans contractor support, equipment solutions, technical training, and a wide range of HVAC applications, including ductless, dual fuel, geothermal, and hydronic systems. So welcome, panelists. Okay, so folks, we're going to be I'll be facilitating a discussion with these panelists for the next 45 minutes-ish, and then we'll open the floor up for some Q&A. Also, if you've joined us before, you're familiar with this process, but near the end of our session, you'll see a feedback poll pop up on your screen. That's just to get some insights on what went well today, some suggestions for future topics and formats that we could consider. So please do put some thought into that. We really do look at all of the responses. I'm going to just start kind of with a broad question for all panelists. So just to get some insights into what you're all seeing in the field right now. So what are the most common disconnects you see between how HVAC systems are designed on paper and how they actually perform once installed? So maybe we'll start with you, Bryan, hear from you, and then call on the other panelists.
One thing we've noticed on the callback side and the wholesale world is what that comfort advisor might discuss with that homeowner at the time of the kitchen table when they're figuring out what system to put in and listening to the homeowner's needs is if they don't have that 30 to 35-minute debrief with the technician who's going to do the install. That's a big disconnect that we've seen just for overall comfort of the home and what that homeowner was expecting the system to do versus the actual reality of what got installed.
Great, thank you. Village Mechanical team, what are you guys seeing?
I think I might refer more towards like our specialization is geared towards retrofit installations. We don't typically work with any new builds, so everything in our perspective comes from a retrospect perspective. So one of the main disconnects is actually within the conversation with the homeowner and the lack of awareness of what is involved with a retrofit situation that may involve electrical capacity calculation. Because it is a retrofit situation and the home is already built, the systems are already in place, there's a lot of constraints we are having to work with and work around. And so understanding where an indoor placement and outdoor placement of units can become a very complex conversation. And so it's more around what are the constraints and understanding those constraints and working around that with the homeowner. Do you have anything to add?
Nail it. No.
Perfect. How about you, Dara?
Well, we don't deal with we don't deal much with retrofit, or if we do, there's some renovation going on. What we find is that as designers, from a designer point of view, a lot of installers are reluctant to call a designer when they run across something in the field. Or there's a customer makes a change request, or there's a framing issue or something. They go by guess and by golly and try to make it work. But we're there to support them. So if they call us, email is better, and tell us what they want to do. Then we can tell them what works and what doesn't. And it's the lack of communication that leads to issues. And that, if there's a problem later on, and we are called in, and say, well, can't do anything about it now, it's done, or this is what you've got to do to fix it, and it's got to be expensive, and it's going to be expensive. So communication is key for us.
Right from the get-go.
Right from the get-go. I mean, this is kind of your run-of-the-mill job, and we do have projects where the customer is willing to pay us to go out and review the system while it's being installed, and we're doing commissioning, startup, and final inspection. That's most people don't want to pay for those kind of things. But just your run-of-the-mill job, new install or renovation. It was very common now, additional dwelling units, expanding out over the garage, extending the existing system. It's not so straightforward when you get on the site to do the install. But it's a fundamental step the installer needs to understand. They can call us up and get an answer, and ask us questions about alternatives, and we're there to make them look good.
Great. And Rob, how about from your perspective? What do you see?
You're muted, Rob.
Probably better off muted. I think that biggest disconnect from the design to the actual execution of it, I guess I see a bigger thing. I think it's the culture of installers, and I have to be clear. I came from the installing side. I have several trades tickets, and I work with a tool belt on my waist for a lot of years. I come from the contracting side, so I get it. I get the things that are going on there. But what happens often is I go to site for site review, and I see something that's not as designed to ask about it. What I'll hear is, we've always done it that way, never had a problem. That's the kind of stuff that I think sort of represents a culture, that culture without standards of practice. And I think that's the biggest issue. There's not really, thank goodness there's a lot of great contractors out there, but they're the minority. They are the minority. And I think that's the biggest issue.
Okay, great. Thanks, folks. Okay, so we heard a lot from Rob around right sizing heat pumps. So maybe Rob will give you a break on this one. But as we all know, right sizing continues to be one of the biggest topics in residential HVAC. So, what are the most common mistakes or misconceptions you've seen around sizing heat pumps for high performance homes or in retrofit scenarios as well? So maybe we'll start with the retrofit scenario and pass things back over to Village Mechanical.
I just want to make one more comment to the last question in regards to common disconnects, because we're usually the contractor that gets called after the system has all been installed and the new home has been built. And one of the main things that we get calls for is controls. So oftentimes systems haven't been properly set up after installation. Most of the time it's because an understanding of how the system was supposed to be set up wasn't understood in the setup process. So the controls and, as Rob was mentioning about balance points and the switchover temperature, they're not actually set up properly. So that's one other comment I'd make there. With regards to right sizing, again, talking more about retrofit situations, we're again approached through the process of constraint. So even if we get a heat loss calculation that says this home requires 36,000 BTU, we are limited to the size of the ductwork, we're limited to the electrical capacity, and so maybe the ductwork requires more airflow than what a 3-ton unit can provide, or vice versa. Or maybe there have been a number of situations where the heat load calculation requires a larger unit, but the ductwork can't support that size. So you have to undersize the unit and add auxiliary heating. So there's a number of different variables that can affect right sizing in that case. Anything else?
Yeah, no, I just like with regards to the aftermath of installs and design, it's a lot of the time it seems with new home builds, power and control lines are being run before there's an understanding around exactly what the equipment requires, because there's so much new equipment and I guess new ways of designing these heat pumps, and in a lot of cases dual fuel combos, and then maybe they pull too few control wires to the thermostat area, or too few control wires between the indoor and outdoor, and then it's pretty obvious when you show up afterwards they've just made it work instead of going back and pulling it, and even in some cases undersized power feeds to the outdoor unit. So
Great. Bryan, are you seeing similar things over there?
Yeah, very very similar on there. Is we have seen it where the heat load will call for a 36,000 BTU system, and the ductwork can't handle it, and that unit goes in anyway. And then the homeowner just has a terrible go out of the gate with it, just simply because it's too loud for the ductwork. It can't handle it, and then it's short cycling, and it just adds problems to that end user. So yeah, that's one of the major ones we see is quick install, quick design, and lack of follow-up for an end user. But even on some new construction, we've noticed as well that certain installers haven't stayed up on technologies that changes in the marketplace. So that same 3-ton system they've been putting in for the last 5 years in these houses, with the new efficiencies of a lot of the side discharge heat pumps versus the traditional top discharge unitary system. You don't need the same 3-ton. You could drop down to a 2.5-ton for those homes. So a lot of it is sometimes the installer does need to really focus on the brands and follow up with the new training and the products that are available, because it's rapidly getting better and better for each brand that's out there now.
Great, thanks, Bryan. And Dara, what are your thoughts around most common mistakes or misconceptions you're seeing around right-sizing heat pumps?
I agree with what everyone else said. I don't know, it's not mistakes so much as when we have the opportunity to find out what equipment I mean, a lot of times we do a design before we know who the installer is. But sometimes we do a design when we do know who the installer is, or the installer comes in, after the design is done. And it's a question of asking a simple question. Well, you're going to be installing the system. What equipment are you comfortable with? Because you get mistakes when the equipment specified is not something the installer is familiar with. He doesn't have supply chain support for it. And then he goes into by guessing by dollar note again. So from our point of view, it's important to, when we can, to specify equipment that the installer is comfortable with, and that he can get supply chain support. It goes to you, Bryan, that if you're working with an installer and you can support him, then everything goes better. But if he's just buying the unit and he doesn't have that support, then there are problems which can't be solved, or very difficult to solve.
Okay, thanks, Dara. All right, there were a couple comments there around kind of challenges with ductwork in existing homes, and how sometimes the solution is installing auxiliary heat too, and that ductwork is too small to accommodate for the required size of the heat pump. Just wondering, and maybe this will just be an open question to anyone who has thoughts on this. Hop on in. Rob, I see you unmuted.
It's the same thing that was just discussed. What in a retrofit, what you've already got is what you're stuck with to some degree. I mean, there's little tricks you can do. Usually a tight little furnace room, for example, in a basement is adjacent to common areas like a hallway or some other room. You can access the duct that's available, put in a return or a supply. Usually basements are don't have enough return anyways. That might give you a little bit of reduce the friction system, give you a little bit more room to have the size of system that you want. Other things you can do is dump zones, bypasses. They help with restrictive air duct work. The other thing is, you put in a smaller system, you can put auxiliary heat, but if, say, for example, you got that bedroom far away above a garage, it's never warm enough, never on, and it's always overheating. Maybe there's an opportunity to put a ductless split in that room. Just mix it up, get creative. There's a lot of things that you might be able to do, and I think any contractor knows that those challenges do restrict your options compared to new construction. But there are things you can do. And the fact that we're transitioning from dual fuel to heat pumps, really, it doesn't matter what kind of heat pumps, it's always going to be the same issues. Even putting a new dual fuel system in an existing home is potentially an issue if the ducting is undersized. And that's a critical thing, is to check that ducting before you commit to anything.
Yeah, so adding to what Rob was mentioning about checking the ducting, for the HVAC contractor, when they're doing the site assessment in a retrofit case, is getting those static pressure and airflow measurements and seeing what is actually happening there, and figuring out what options there may be for new ductwork design around the supply and return ductwork and around the new systems. So there are some options around there, but we first need to get that static pressure and airflow measurement, which often gets missed in the first site assessment, site visit. I also want to circle back, if we have a minute, to go back to the right sizing question, as Sean has a quick comment about that too.
Yeah, just to add to what Bryan said earlier, a lot of the new equipment, I think Rob also touched on this, you can't size it the way you did old equipment. The new equipment has a lot of bells and whistles, vapor injection, things like that, so it runs well at lower temperatures. And if you just go by their nominal tonnage, a 3-ton or a 4-ton, a lot of them, actually, I'd say most of them that I've seen, a 3-ton will put out more than a nominal 3-ton amount, even at -10 or 15 degrees C. So finding the extended manufacturer heating data and cooling data for these is, I don't think you can size one of these new systems without that extended data. I've actually just recently learned that even the HRA data, where there's some standard tests done and outputs for usually I think around 47 degrees and sometimes at 5 degrees. When they do those tests, they actually lock the system into it's like regular 60 hertz and 100% output. But these units, because they're all modularly driven, if they need to, they can run at like 110, 125%. They can modulate down to 20% as well. So sizing it from the manufacturer's data, the extended data, is really the only way to do it. Even just taking 2 data points and drawing a linear line is not correct. A lot of these, because of vapor injection, could actually put out more heat at -15 than they do at -10 because the vapor injection is kicked in. So technology has changed the game so much. We need to really be careful where we're getting our information from on how to match these up with the size needed for a home.
Thanks for that. And you know what, I might actually keep the focus on you folks over there at Village Mechanical as we wrap this section up, because you are our northern representatives on the panel, and I know that that a lot of what you're just talking to and a lot of questions that we get and have been already getting today are around kind of cold climate heat pumps and their efficacy in our colder regions. So I just love to hear your perspectives around the skepticism that does exist in these regions, and what building professionals should understand about modern cold climate systems and how they perform in extreme temperatures.
Well, as Sean was just mentioning, when you speak with manufacturers, absolutely, I ask for their extended data performance charts. Do not rely on HRA numbers, because again, it's a standardized system testing, which locks in the systems in certain points so that they have that standardized practice. But these manufacturers have significantly different performance data than what's actually provided. So when we come into something like cold climate heat pumps, there's a lot more performance output at cold climates that at this point, I don't understand why any installation at this point wouldn't be a cold climate unit. I believe, or we believe, that pretty much every unit that should be installed at this point should, in this region, not just in northern region, but even mainland Vancouver, a cold climate heat pump will meet design temperatures. It's only in very, very extreme cases where you might need a dual fuel system, say like Tumbler Ridge or Prince George, where they have outdoor design temperatures at -35 or -38. You will certainly need a little bit more of that auxiliary backup or dual fuel system. But everywhere else, even where we're located, our design temperature is -19. we are fully able to electrify with a fully electric cold climate heat pump without any backup auxiliary or dual fuel system. These cold climate units are performing at their rated capacities, rated outputs, and we have not received any issues with what we've installed, and we've installed quite a few of them around here.
I'd just like to add to that. If someone has had a cold climate unit recently installed and the homeowner is saying, oh, heat pumps don't work in these temperatures, it's not the heat pump. It was either incorrectly sized or they did not purchase a heat pump that was meant to go down to those temperatures, or most commonly, it's just hasn't been installed correctly. If you install these correctly, they do exactly what the manufacturer extended data says that they're going to do. And in terms of brand, I know there's a lot of brand wars out there right now with this, but I'm a firm believer there's very little difference in the brand of unit that you buy. I'd say 98% of all the issues with heat pumps come down to installation, sizing and installation. You can buy a cold climate heat pump off of an internet site, and if you install it correctly, it is going to work well. Now, it might not have a bunch of bells and whistles, and you might get a couple of years less use out of it than a high-end model. But if it's installed well, I mean, the vast majority of these are being made in one of like 4 places on Earth. So, chances are you just got a variation of another brand.
The perfect segue into my next question around what installation challenges are you seeing as they relate to retrofits in rural and northern communities, installation challenges that are most commonly affecting system performance then?
Well, with installation challenges, with heat pumps, there's many different components already identified that Rob mentioned, where you have to bring in this whole IDP process. You've got your electrical, you've got your energy advisor, you've got your ductwork design and ductwork fabrication. If you're doing a fossil fuel conversion, you need to make sure you have a gas fitter, a ticketed gas fitter. So that's there. And then you need your Rackham trades person that understands proper refrigerant installation. Not to say that in a Part 9 building, I know that there's some training going on for gas fitters, plumbers, and a few other trades to allow them with the installation of residential heat pumps. But there's just so many components and parts to an installation that to bridge them all together and have that working conversation, it can cause some of those disconnect pieces. So in our area, when we don't have all of the sub-trades and access to sheet metal fabrication, or, our energy advisor is not always available because they have so much other things going on, that, a single HVAC contractor in a northern region doesn't have all the resources that, say, someone in mainland Vancouver has. So we're pretty much the place of having to be an expert in all of the fields. That then becomes quite the installation challenge. So either you become an expert in all of the areas, or you're trying to coordinate with all of the people, and then that also becomes the installation challenge.
Great. Great. Thanks so much, Joanie and Sean. We're going to move over to Bryan. So Bryan, you've seen this industry evolve significantly over the last few decades, I imagine. So from both the supply and contractor sides, and just focusing kind of on technology trends that you're seeing shape the industry. What technologies or system approaches are you most excited about right now? And what trends do you think building professionals should be paying closer attention to?
The one that I'm really excited to see is we're finally seeing the air to water explosion of manufacturers hit our region. For the past 10, 15 years, there's been probably a group of manufacturers I could count on one hand that had air to water in our market. And it was a very expensive way to go to do those types of systems. And I was just at the heat pump symposium last week, and the amount of manufacturers this year compared to just 2 years ago that have launched their products that they brought over from Europe and Asia that they've been using for dozens of years is so exciting to see. And for builders, we're seeing more builders asking about the air to water and how it can fit into their homes, because it does give them unique opportunities to, to upsell a standard home if they go air to water, if they're doing in-floor heating and domestic hot water and, heating and cooling the home. So air to water for me is where I see a huge direction of this market going, because as a retrofit, you can remove that gas hot water tank and that tankless gas fired one and go all electric. And the nice one is there's so many new options that are coming out. Is I think the technicians and the builders are going to be inundated in the next couple of years with training opportunities and info sessions to get up to speed with this technology that's finally arriving.
Forever something new to learn. Great. All right. So around I know we all have wherever you are kind of across BC, and I know there's folks across the country, we're all experiencing different supply chain issues for various reasons. So how are you seeing contractors and designers adapt to these supply chain challenges or rapidly changing product offerings?
I think the main one was we've seen some manufacturers that have never really recovered from COVID. It threw a complete wrench into so many different supply chains, and some haven't. I think what it forced, contractors and the designers was they had to go in with, 2 or 3 different options of equipment, just to make sure that, if they were awarded the job, they could, install it. But on the flip side is it did give them more opportunities to learn what system would fit best, because not every manufacturer fits every home. And I'm a real believer that, the installers and the builders, they should have a couple brands they go with, because if you're just going with a single source like guys did, 5-10 years ago, that's a drastic difference than now, when most of those builders and designers that are going in, they'll have 2 to 3 different brands that they'll work with to look for that fits that application best. And I think that's the shining light out of the supply chain issue, but it really forced the installers and everyone in the industry to kind of change the way they look at the market, because like I said, we've seen some manufacturers that have never truly recovered from the big disruption a few years ago.
Great. Thanks, Bryan. All right, over you to Dara for a couple of questions. So Dara, your experience spans kind of comfort, indoor air quality, ventilation, and mechanical systems over several decades. And as we know, a lot of HVAC issues only become visible after occupancy. So we're going to focus a bit on commissioning and system performance. So from your experience in commissioning, quality assurance, and fault investigation, what are the most common issues that prevent systems from achieving their intended purpose?
Actually, the outlier is duct leakage. If it's installed according to the design, but the ducts aren't. The ducts leak air, it's not going to work the way it's supposed to. It's just kind of a trauma problem. I think, in other areas where the sheet metal installer is responsible for work, but there's the problem in Toronto with merchant built homes where the sheet metal installers are unionized, and they get paid by the number of branches in the house. So our saying is, the problem is that the individual is paid by the number of branches they can get to hang in the floor joists before they get out to the truck. So the sloppy work leads to duct leakage, and if the air leaks out before it gets to the end of the line, the system's not going to work properly. I've tested systems that were done by an old school sheet metal installer, the kind of guy who dollies the joints in his takeoffs before he lifts the duct. And the leakage was close to 10%, which is what we should expect on all new systems. When I've tested ductwork on a unionized job, and the people didn't care, they were just there to hang the ductwork and get out onto the next job. And the leakage was more than 50%. So more than 50% of the air never got to the end of the duct. And particularly for rooms that are a distance from the equipment, it's a disaster. Thankfully, here in Ontario, there are people who do air seal, which is I don't know about BC, but air seal is the proprietary system where they blow kind of aerosolized bubble gum into the ductwork, and it seals the gaps. And it's a tested result. They use the same methodology, and it's in a lot of cases it's a lifesaver. We have a home, and it's finally built, and there are comfort complaints, and you go and measure the airflow coming out of the registers, and it's not sufficient. And then you go in the center and say, well, it's moving enough air, but the air is just not getting to the end of the duct. The problem is leakage. Either care and attention and install, or have the ducts air sealed.
Great, thank you. And Rob, I think I saw you nodding your head saying that solution exists in BC as well.
It does, yeah, but we actually put very specifically in excruciating detail how we want the system sealed, so it is specified. So if it's not done to that degree on the install, then it's called a deficiency and it has to be addressed, and they won't get their oil back unless they address it. I'm very strict about that. I'm like Dara. I've seen it. We've done lots of duct blast tests where, pressurizing the duct with smoke, and we can see where it comes out. And I swear, if the installer standing beside you when he sees that, that's going to be a life-changing moment for him, because they don't get it until they see it with their eyes and go, holy jeez, that's a lot of air coming out of those joints. I didn't expect that. Every joint, every seam, every gordon, every elbow has to be sealed with either tape, oil tape, or mastic. And there's no excuse not to do that. It's just that is a big deal, as Dara said. If you're losing air through openings in the duct unintentionally, it's coming out the first holes. It's not going to wait till it gets to the end of all that leaky duct to come out. It's coming out, so it's going to over condition the areas closest to the equipment and under condition the areas farthest away from equipment. It's a big deal. So I agree with Dara about that. Now you can get that aeroseal done, which is a good idea when it's too late. The duct's in, it's covered up, drywall's on, it's painted, whatever. You can't get at the ducting to fix the crappy ceiling. So then you can get that. That's a good solution, and it's done in retrofits. It's pretty standard in commercial applications, R3 applications here. I have seen it done in residential applications, but not that common.
Great. Okay, we have a couple more minutes here before I want to switch over to the Q&A. We have a few questions in, so I'm gonna close with a question for all panelists in a bit of a speed round style. We're just gonna provide one practical step builders, designers, or contractors can take on their next project to improve HVAC performance outcomes without significantly increasing cost or complexity. So one quick practical step folks can take home with them. And maybe Bryan, I'll start with you.
Communication. I think that's the key. Is if the builder's relaying to the installer what he wants and expects from the project, or on the retrofit side, that comfort designer, listening to that homeowner, but also sharing back the constraints that they would find with their existing system. Communication to me is the key to alleviating problems or issues down the road without having big costs come back after the system's installed.
Perfect. Thank you, Joni and Sean.
Say take the extra hour when doing a site assessment. Oftentimes there's not enough information collected during the site assessment. People rush through it. So take an extra hour, and what you could do is even charge for that extra hour, but just say, if you want to proceed with this installation, this fee will be credited towards your installation costs. But at least you're now taking the time to collect all of the information needed for a proper design.
Oh, I'd just like to add one thing to this as well. I think it's something that Rob touched on earlier. It's culture. Everybody's just trying to get the job done and get out. And there's one thing I've noticed is there doesn't seem to be a large culture of really appreciating great work being done. Rob also mentioned, like, you can get this really amazing high-end Japanese made heat pump units. The reason they're so good is because of their culture. They won't allow garbage work to be sent out. And I think that's one thing I've noticed being a business owner is in hiring people and having employees is for some reason, everybody thinks fast is good. And I get it. When it comes to money, that usually equals a little more money in the bank account when you get it done quickly and get out. But there needs to be a lot more appreciation for good work at all levels in this industry, and it needs to be said by all different levels in this industry, because if the homeowner doesn't realize that they've had a really good quality job done of any one of the steps involved, how do they appreciate it? How do they understand that extra money was worth what they bought? Or how do they understand that they didn't get what they paid for? So I think that culture is at the very core, needs to change in this country.
Great. Thank you, Dara. How about you? One practical step builders, designers, or contractors can take on their next project to improve HVAC performance outcomes.
Well, I'm siding with Bryan. It's simply communication before the job, during the job, and after the job. There has to be communication between everybody, and that avoids problems, and that leads to solutions. And it's really no cost. You just have to send an email, pick up the phone, ask a question, get an answer, and find out what. I mean, the business we're in is matching the customer's expectations with reality. And if you don't take the time and communicate, you can't do it.
Perfect. Simple as that. And Rob, quickly from you, one last practical step.
Oh boy. I think I think everything I have to say I said in the slide presentation. I think as a contractor, you should just learn how to be a good contractor. I love what you said about the culture, and have a little bit of dignity and try to do well. I think that in order to do that, you have to understand your job, which means you have to educate yourself. And like I said, if you follow those 7 stages, and I've said this over and over again, that's how you're going to minimize costs, because you've got to know where your costs are coming from and how to bring it down and how to align it with the expectations of your homeowner, whether it's a retrofit or new construction. You have to align expectations with cost, and you have to find out where there's flexibility in either the expectations or the budget. And that is, it includes everything that was said: communication, having some self-respect as a tradesperson. Back in the day when I was in the trade, to me, I was so proud to tell people I was in this trade. Not so much today. It's not the same. It's very different. But I think all these things, and have a process, a plan, stick to it, communicate, all these things. Everything that we've said during these 2 hours, I think, goes into it. Not just one
Great.
thing.
Not just one thing. Fair. It's hard to narrow it down. All right, we have about 10 questions left, or 10 minutes left with quite a few questions. So as we go through these, we're not going to have time for everyone on the panel to kind of provide their insight. So maybe if you're feeling particularly inclined to respond to the question, feel free to unmute yourself and jump in, but we'll make sure that we do hear from everyone. Rob, maybe though I know you specifically spoke to IDP. This question came up during your presentation. And there's some research that shows, I guess, that many in the industry do not know what IDP is, and that HVAC trades are typically left out too late in the building process, and just kind of some thoughts around that.
Yeah, that's true. I mean, we have sort of bureaucrat, technocrat kind of vision of what an IDP should be, where a bunch of engineers have never put tools on in their life, kind of telling the industry what an IDP should be. That frustrates the hell out of me. It's basically simply nothing more than a get together of the people who have some impact on the decisions to coordinate with each other and negotiate with each other and bring their respective expertise to bear on achieving a common set of expectations. That's all it is.
That keeps going back to that communication piece. Perfect. All right. If there's anyone, and it could be Joannie and Sean, but who work in kind of parts of BC with no access to natural gas, this attendee is wondering if you'd advise going to a cold climate heat pump capable of operating down to, say, negative 28 degrees Celsius in these colder climates with a propane or strip heating as backup. I know that we did hear that in your experience, Joannie and Sean, you're saying we can go all electric in these colder climates, but wondering if you've ever considered kind of that propane or strip heating backup as another solution.
I'll have Sean answer this one.
Yeah, I would. If I lived in an area that had a design temperature of minus 28, I'd probably put the same thing in I put here, but with some strip heating. I mean, if you consider that design temperature, the chances of it being at that design temperature for the entire winter are these days pretty slim. So even with electric strip heating put in, yes, it's a lot more expensive to run, but you're only going to be using it for most likely a few weeks out of every year. And these new systems, it's not like the old one where it would just switch off the heat pump and turn on these electric strip heaters to heat your home. If you get a matching outdoor and indoor cold climate unit and put auxiliary heat in it, it stages the heat to top up what the heat pump is still doing. Most of these heat pumps will run till minus 35 and colder. Of course, their output is reduced, but the heat, the auxiliary part of it is just there to top it up. It's not like an older traditional system. So you might end up with higher bills for like a month out of the year. And then the other 10, 11 months out of the year, you have this heat pump that's more than capable of meeting all of your heating and cooling needs. So yeah, I wouldn't hesitate. I think in some areas too, depending on the situation, propane might be a good idea, but I think that's very specific to where you are and what you need for your home.
Great, thank you. All right, maybe I'll open this up to whoever feels like speaking to it. But Ryan asks if a combination of space heating and hot water systems is more cost effective or separate systems more cost effective, and how about redundancy and reliability between the two as well?
I think that's the hesitation to answer that is because it's a question like how long is a string? It depends on the situation, and there's an awful lot that goes into figuring out which is the best. I don't think there's a simple answer to that at all. It could be the better way to go to have them integrated. It might not be. It depends on the situation, and that's the whole point of doing all the things that we talked about, especially communication. Figure that out and do some cost benefit analysis. It doesn't have to be a 10-page report. It can just be, a little bit of math. But it is possible that it is the best, depending on the situation, best option. In other situations, it might not be. Depends.
Okay. It depends. All right. We have two questions that are actually quite similar. So they're both around situations where where central ducted heat pump installation results in temperature stratification through the home. So say a cooler basement and warmer upstairs. And I know that we talked a little bit about this with ductwork installation. And so one person's asking how you tackle that, and another's asking whether dual smart thermostats and dual dampers. Oh no, sorry. I think that they were combining multiple questions. We're just generally asking advice on how to tackle that then.
Yeah, my first reaction is that's a common symptom of ducts that leak too much. That if it's cooling and the basement turns into a meat locker and you can't get it cool enough on the top floor in a two-story home, that's duct leakage. Assuming the system is properly designed, because in the winter when you're heating, heat rises. So when you do need a substantial amount of heat in the basement. So your upper floors wouldn't be fine, but in the summer, if the air that's supposed to go into the top floor, most of it except in the basement, because that's where most of the ductwork is, and that's where most of the joints are. It doesn't go anywhere; it stays in the basement. So I'd say your first step was to look at the duct leakage, and then you could look at zone control, or if you can't address the duct leakage, that kind of solution can be an option. But the problem with applying motorized dampers to, for instance, if you apply them at the end of the branches in a leaky system, it doesn't, or if you're trying to balance a leaky system, people ask us to go balance the system. We do a system test. We say your duct leakage is too high. It's not pointless to try to balance, because the more you balance, the more leakage you're going to get. We start closing dampers at the end of the branches, you get more leakage. So my response to that is look at the duct leakage. Fix that first.
Just to add to that, at least from a retrofit perspective, in our experience, a lot of it, we can't do anything about the ducts. They were put in a long time ago and they weren't designed. Return air is a big issue. A lot of basements don't even have return air cut into the ductwork. They're not even pulling air from down there. So that can make a big difference to bring some of the air out of the basement and into the system. The other is air circulation. Standard furnaces, have an on-off. They crank out a whole bunch of heat and then they stop and they just sit. And, the common room upstairs with the thermostat's usually the last place to get cold while the rest of the house freezes. So one of the nice things about the new cold climate systems of many different brands, they all appear to be doing the same thing when you match an indoor air handler with an outdoor unit, is the outdoor unit will modulate as well as the indoor unit. The indoor unit has multiple fan speeds. And if you get a system that has a communicating thermostat, they use their algorithms to determine how much air and how much heat need to be supplied to that house at any given time. And what ends up happening is the fan and the compressor run a lot more of the time, but at very low rates. And the number one piece of feedback that we've got from people that we've installed one of these systems in place of a gas furnace is, I can use my basement in the winter now. The difference in stratification because of how those new systems work is probably the most noticeable thing by the customer. So, you know, cut some return air in, consider how your approach to heating the home is being done and with what equipment. And if that still isn't meeting all of the needs of certain rooms at the far end of the house, there are some small solutions that you can buy for under $100. You can replace the grill on a diffuser in a room with a little air booster. You can plug it into a 120 volt socket, and it some of them are on off, some of them sense temperature difference and will automatically come on when it senses that the heating or cooling system is trying to do its job. And it will boost the air coming out of that duct without doing any major invasive retrofit, challenges. A lot of the time, people that have 3-story homes, I've suggested these duct boosters to be put on the top floor in summertime, because it's very hard to push cold air to the 3rd floor, and most people have had a lot of success with them. So those 3 things: air circulation, how you're approaching heating and cooling your home, and return air, from our experience, has been I'd say the 3 biggest factors in getting rid of that stratification.
Great, thank you. Okay, that does just bring us just over time. Rob, I wanted to quickly ask one question that came up during your presentation, just a super quick response, but I found it to be quite an interesting question. Greg asked, when replacing an older heat pump with a newer cold climate model, for example, is it possible to reuse any of the existing indoor components rather than replacing the full system? So the purpose
Yes,
here
it is
would be-
possible. It
Okay.
depends. Yeah, you can get an outdoor unit with a coil that you put into an existing plenum of an existing furnace, given that you want to keep the components relatively new, well maintained. Yeah, that's a very reasonable, viable option. So the absolute answer is yes, you can.
Okay, perfect. Okay, and folks, I know we didn't get a chance to answer all the questions. I know there were some pretty specific project specific questions there. I wanted to make sure we answered the more broader questions first. I want to thank the panelists very much for all of your insights and your perspectives, and everyone on the call for your participation and your great questions. I'm just going to close really quickly here by giving a thank you again to our project and our webinar funders and sponsors, and just to close out by mentioning the Home Performance Contractor Network. If for those of you who are working in the retrofit space, if you aren't familiar with this network, this is how your clients can access the available provincial and utility rebates. So you can connect with us for more information there, or Home Performance Contractor Network directly at info@homeperformance.ca. All right, so with that, another big thank you to the panelists and to everyone on the call. And yes, I hope everyone enjoys their beautiful spring day.